power of HSS in SolidCAM 2015, and it will be given by Ahmad Onkar, who's the product manager for 5-axis simultaneous as well as HSM and HSS, and is also a very world known in this particular field. So everyone can just sit back and relax and watch the webinar, and of course there'll be time for questions at the very end. So Ahmad, I will now make you presenter, and you will be able to start the webinar.
Thank you very much, Sydney. Hello everyone, and welcome to this webinar on HSS. What I'm going to show today is how we are going to use HSS to complement the existing modules of SolidCAM, for example, 2.5D or HSR or HSM. How you will see that without HSS, it's like being incomplete. It's like missing one of your fingers. So HSS completes the circle for 3-axis machining. So what you're going to see in the next 45 minutes basically is that you will look at various things that HSS can do, where you will find a lot of limitations which hamper you, or which do not allow you to do the things the way you would have liked to done using HSM or 2.5D. So HSS is basically that link, that strong link between the other modules of 3-axis or 2.5-axis in SolidCAM. Right. Let's first understand what HSS is all about. HSS basically is a high-speed surface machining module inside SolidCAM, and it works directly on the NURBS data. Now, what do I mean it works directly on the NURBS data? It means that unlike HSM or HSR, we do not create any intermediate mesh or triangulation and machine the triangulation. What we do directly here is we pick up the surface as it is and machine the surface. It's either a single surface or a group of surfaces. So the first key thing here is it works directly on NURBS data. Now, because it works directly on surfaces and not works on, or does not work on triangulation, the issue of gouging comes up very quickly, because when you have a triangulated model, generally you'll see that the tool paths are gouge free because it's a simple check for it. If you're using a ball nose tool on a triangulated mesh, it's like checking the collision of a sphere against a simple triangle, which is a very simple equation, and things happen very quickly. However, when you're machining a NURBS surface, it's a different ball game altogether, because you're using the sphere and you are checking the collision against every point on the surface. Okay, so it's it's a much complex situation. In spite of that, some amazing and powerful gouge check options are available inside HSS. We are going to see a few of them today. Every time I'm going to explain to you, I'm going to bring up the the issue of triangulation. We know that when we import a model inside any software, let's say through IGS or STEP, there are bound to be issues with the surfaces. You could have wrong trimming, so one surface could be overlapping onto the other. Okay. Now, this problem is actually taken care of very nicely when you do a triangulation, because a triangulation doesn't care about what is below. It only cares about what is there on top. Okay, so if there is any overlap, the triangulation nicely covers it. So the issue of overlaps and gaps actually doesn't arise when you're using triangulation. However, when you're using a NURBS-based system, which machines only NURB surface and doesn't generate any kind of triangulation, we have to understand here that you're going to have these problems that the surface might have gaps, they might have overlaps. Now, how do we take care of these? These are nicely taken care inside HSS using links. Okay, we'll also see that issue. Generally, HSS is used only for local area finishing. Only in some cases you will see that it will also be used for roughing out certain areas. Otherwise, broadly speaking, 99% of the times, HSS is used only on local areas. For example, you could have fillets that you need to machine. You could have chamfers that you need to finish. You could have ribs that needs to be done, or you could have undercuts that need to be done. So only some local area finishing is taken care by HSS. Now, these are those areas, although they look very simple, you will find it exceptionally hard to use any other method to finish them. We are going to see a few examples why they are so hard. Now, because it's working on NURBS data, you get an exceptional surface quality. I'll show you a part that was completely finished. It's actually a mold that was completely finished using HSS. Each and every surface was machined separately, and I'll show you the quality of the surface that has come out on steel. And it is an excellent complement for 2.5D machining, eye machining, and HSM. Okay. Now, with this as a background, what would be the key strengths of HSS? The first one is you can use almost any kind of tool inside HSS. You could use a standard tools, or you could use shape tools. Okay, I have put up a few shape tools. For example, a torus cutter, a lollipop cutter, or a dovetail cutter with a radius. You could use them in machining undercuts, or you could use them on a regular surface itself. Undercuts machining can be done using shape tools, because you can't use the standard tools to machine undercuts. Okay, that's not possible. So you need to use shape tools. Exceptional surface quality and working on selected surfaces only. And the most important thing, it's actually a boon to the programmer, because whenever you want to machine a small or a local patch of the entire model, you need to define boundaries, right? So with HSS, we eliminate the need to define any kind of boundaries. You don't need to define any kind of boundaries in HSS. Right. So question now arises, why do we need HSS? Okay, we saw that, we learned that it is a NURBS-based system, works directly on the NURBS data. It can work on patches of data. Okay, it can handle undercuts. Why and where is HSS used? The very first example that I'm going to give you is the part that I would like to show you somewhere in between our webinar today. And this was a part that was done completely, or finished completely using HSS. We did it because certain areas, for example, I'm not very sure if it's going to be very clear to you, but I'll try and make it as clear as possible. I've marked an area here. Okay. If you look, or if it's clearly visible, there are marks remaining on the floor of the part or the mold. What has actually happened here is, when we used HSM, this area is very tight. It's like almost 11.5 millimeters in width, and we were using, I think, about 10 millimeter cutter. So whenever the cutter used to leave one of the wall and go to the other wall, there used to be, the tool was always deflected. So whenever the tool left the wall, it used to come back to its original state. Even a small one, like 50 microns of deflection, is good enough for it to start creating marks on the bottom. Okay, so the end result was a really bad patch of surface that was left out after we finished the mold. Of course, it's not presentable, but there's not much you can do when you're trying to machine a mold completely, right? There's not much you can do because you would like to define a boundary, you'd like to define the tool and say now machine the surface with two different things, constant Z and linear. You provide the slope angle to it, and using the slope angle the system decides which is horizontal and which is vertical and applies the strategy accordingly. And one of the final results is you get patches of areas where it's too tight for the tool to retract and go to the other wall. So whenever it does that, that small deflection is enough to create problems on your floor. The same area was then resunk and machined with HSS. This is the same area. You can see there's a major difference in surface finish. First of all, you can see that, or when I show you the file, you'll notice that the entire part was machined surface by surface. Okay, it's a very old school of thought because in the earlier days, let's say in the late 80s and early 90s, when CAM was still evolving, there were systems like computer vision, SmartCAM, etc., and they had this principle of machining surface by surface. Okay, the finishing used to be done portion of the surface, another portion of the surface, so on. A similar principle was used here to machine this using HSS. Everything, including fillets, including the floor, including the wall, were machined separately. Okay. Now, what is most amazing here is, if you can look at this figure out here, where my pointer is, you will see that that's the point where 4 fillets are actually merging. There are 2 male fillets and 2 female fillets, and they're merging together into that area. And this merging is really exceptional. I remember in one of the exhibitions in India, we had displayed this particular part at a booth of a machine tool vendor, and few of the competitors of that machine tool vendor came with a small pin, and they wanted to check if there was any dig mark in that, and they were amazed to find there's absolutely no dig mark. It was a perfect CAD merged, like as if somebody has done some modeling on the part. Okay, so the difference of surface quality between what we saw in HSM and what we see in HSS is remarkable. You can get phenomenal surface quality with HSM, but with HSS it's really exceptional. The only reason being that we are cutting directly the NURBS data. Another example that I would like to give you is one of the parts again of one of my customers, which was completely finished using 3 different methods. First of all, the roughing was done using iMachining 2D and iMachining 3D, right? And then we finished the floor of the horizontal areas of the part using HSM, and some vertical portions using HSM. So we used the floors, the flat areas or the horizontal areas, and the vertical areas of certain areas. We finished it with HSM. However, there were several portions of the part where we thought that HSM would be less effective and HSS would be more effective. For example, the top ribs was most nicely finished using HSS, and the biggest point here was there was no need to define any kind of boundary. We just had to pick the surface, apply the strategy, and you had the tool path. And the best part of HSS is everything inside can be controlled by the user. Okay, so the user has an amazing control over the entire process of machining. So you could just pick few surfaces, define the strategy, and your toolpath is done. So first of all, it's very productive. What do I mean very productive? When I say very productive, it reduces the fatigue of the programmer, because when you try to create boundaries, people who have created boundaries will nod their head with me that it's not that easy to create boundaries unless and until it's a flat surface. It's very easy. If there's a curve, for example, if there's a fillet and you would like to create a boundary for a fillet, then it's virtually difficult, very difficult, and that leads to programmer fatigue. We eliminate that fatigue with HSS. Another example was this mold finishing. You can see on the right-hand side the finish that was achieved with HSS. The entire mold was finished using HSS. Each surface, each fillet was picked up individually and machined. Even the mergings between that fillet and probably the other surface was nicely done. That's because we have amazing control over what we are trying to do and how we are trying to machine a particular area. We have always seen, it's been my experience, that whenever you try and machine a particular surface along its flow lines, along the U and V lines, you always get an exceptional surface finish. Okay, it's not very easy. It's not easy at all to actually machine every surface along its flow lines. I remember, again, way back in late 80s and early 90s, we had systems that were following it, and then CAM evolved. A lot of things became completely automated, and the concept of machining surface by their ISO lines or UV lines disappeared, and the entire surface model was triangulated, and then we started machining the triangulated model. Okay, but this particular model was done because the customer had a complaint saying that he wanted to see amazing surface quality on that particular machine, and we did the entire machining using HSS. For example, the roughing again was done with iMachining 3D, some portions of the outer machining being done with HSR. We did the semi-finishing with HSM. In fact, I'm going to show you even in semi-finishing, you can see that problem that I showed you in the beginning of the photograph. So we did the semi-finishing with HSM, and then the complete mold was finished using HSS. Each of this fillet, each of those walls taken up separately, each of this fillet, completely separate. We picked up each surface, and each surface was finished individually. People would tell me that it did take a lot of time. Yes, it took about a couple of hours for us to finish this entire part, but the result on the machine was worth looking at, because we had two distinct parts, one completely finished off with HSM and one finished completely with HSS. The result was, I can say, dramatic in terms of finish. So you can see that every portion of the model was picked up individually and machined. I'm going to show you this part also on how we perform this machining. Another example which I can share with you, or I can tell you why you need HSS, is this particular part. Okay, this was on a 4-axis indexing, and the customer actually wanted to finish also this particular fillet. You can imagine if I try to finish this fillet individually with HSM, the amount of time that I'm going to take, first of all, to define a boundary. Number one, you define a boundary and then you try to machine it. You're not sure you're going to cover the entire fillet. You probably might stop short, and then you increase the boundary, you overlap into the other areas that are already finished. So you have to be very careful in the way you define a boundary, and that takes really long time. But this was completely solved because the customer was very particular that he wanted to see this area finished separately. So again, the roughing and finishing was done with HSR and HSM, the complete area, and only the fillets then needed to be complete finished with HSS. So you can see how important HSS becomes. It's like an important link that unless and until you don't have HSS, you are not really confident that you can completely finish a part inside SolidCAM. So you will need HSS on one part or the other. You will need it probably 5% on one part, and probably on the next part you could use it as much as 60-70%. In some parts we have even used it up to 100%. If it's an aerospace frame kind of part, generally we use HSS almost to about 80-90%. So there is a lot of scope for using HSS. What are the key benefits that you could get using HSS? First of all, the main part is you could machine any kind of part. There will be no area on the part in 3-axis left that cannot be done or cannot be finished with the combination of HSS and HSM. So you can actually complete this entire thing using HSS and HSM. So HSS is a pretty important link. If you're cutting a lot of undercuts, generally people end up spending money on multi-axis machine. Even though it's positioning, they still use multi-axis machining just to make the undercuts. I'm going to show you a portion of an aerospace part where we have done undercut machining using HSS. So you can actually save your money on those machines. If the undercut doesn't need multi-axis machine, it can be done using 3-axis, great. HSS can help you do that. The best part about HSS is its amazing amount that it absolutely needs very low support. Okay, unlike the kind of support that probably you might end up needing on the other modules, HSS, the amount of support that you need from your reseller is really bare minimum. Once the training is done, once the parts are clear to you, you actually don't need much support from the reseller. Surface quality is amazing. I mean, you have to actually cut a part to believe what I'm trying to tell you, because you will only believe it when you see it on your machine that the surface quality coming out of HSS is exceptional. Okay, and I'll show you how we can control even the surface quality if you want really good surface quality, or if you can live with an average surface quality, you can even do that kind of a control inside HSS. And the best part for a customer is the ROI, very fast ROI. Cut few parts, you've already recovered the cost of HSS. Okay, let's see some of the parts or what HSS can do inside SolidCAM. Okay, the first one I'm going to pick up, open, is obviously the part that I told you that was completely finished using HSS. Okay, so this was the part that's done using iMachining 3D, HSR, HSM, and finishing completely done using HSS. Okay, let's look at the toolpath of HSR or HSM, and let's go into that area. Okay, this is the tight area that I'm talking about. Okay, you can see that there is a retract. Okay, if I slightly rotate it, although it will be very difficult, let's zoom into it. You can see that there's a small retract and the tool travels to the other part of the wall. Now, looking at theoretical possibility in this, there's absolutely no way you could actually end up getting those lines that I showed you in the photograph. But we need to be a bit pragmatic. We need to be realistic that the tool here, even though it's lifting up, is still loaded. So as soon as it is released from that wall, it tries to go back to its original shape. In doing so, it actually slightly rubs on the wall, on the floor below. Although it's leaving material, but in some cases, if the tool has been loaded too much, then it can actually dig into your wall in a very tight space. I'm talking of very tight space. If it's not a tight space, then it doesn't matter. It won't make that issue. So in a tight space, when it's trying to do this, and when you have this link, you could see scratches like marks coming on the floor. You can avoid it, of course. You can actually separate the machining of one wall and the other wall. You can make them completely separate using boundaries. But then again, it's a lot of work, correct? So how did we manage to tackle this? We managed to tackle this using, like what I said, HSS. For example, you can start looking at the toolpaths that we generated for this. The first one was for the outer fillet. Okay, the outer fillet completely finished using HSS and spiral cutting. That means once it engages, there is no more side steps involved in cutting the part. The next toolpath was also the flat area here. You can see that each of these patches are machined separately. Okay, we are not continuously machining this. We are handling them separately. And then the bottommost fillet inside. The fillet was machined inside. You can also look at the quality of the toolpath. It's very nice. Okay. And once the internal was done, we go on to the external side. There's another fillet out here. Sorry. That's this fillet that I'm marking right now. This is machined using this toolpath. And then, because you're having a fillet and you're having a flat area, and HSS works, as I said, on NURBS data, remember that you're going to have an edge that's going to be common here between the flat surface and the fillet. And there's every chance that you'll see a small line of material. It could be like 25, 30 microns of material remaining on that line. So in order to sort that out, we used another few passes parallel to curve and overlapped into our flat area. Okay, so that takes care of the fillets, this fillet, surface, the fillet, and the overlap. Once that was done, we go into this area. This entire area was picked up as one geometry, so all this 1, 2, and 3 was done in one go. Okay, because this area permitted us to do it. This whole area was finished using single toolpath. And then we used HSM to finish the floor. Again, we used a ball nose tool. We did not use a flattened mill here because the area was too small to be used for a flattened mill. Again, another HSS, this time out here for this particular feature. Again, another HSM to machine the flat area at the bottom. One more HSS. You can see that we start making, we created almost like about 35, 40 toolpaths to complete this entire part. So you can see that this wall all the way up to here was done using HSS, single toolpath. And by doing it, we actually avoided that problem, which I showed you, because this toolpath has got nothing to do with the other wall. This is only cutting this wall. And it's cutting using the two curves. We morphed it between two curves. And we did one-way machining. So the surface, again, was excellent. And then we went on to the side walls out here. What did we machine? We machined, if I mark the surface for you, we machined these three surfaces using HSS. Okay. The same thing was done on the other side because again it's like a mirror. We did not use mirror, but we just copied it and changed the surface. And the best part was this fillet. Okay, if I mark the fillet for you, it's 1, 2, 3, 4, and 5. This surface was done using this toolpath. Very nice. It was the best part. In fact, it was the best part of the surface of the entire model, which was gleaming with surface finish. And the next one was the complete area out here. Okay. Finishing of the wall one way. Finishing of the fillet, this complete fillet. Okay. And these are the fillets. I told you about an area where there are about 4 fillets, 1, 2, 3, and the other one on this side, the 4th one. All fillets are merging out there. And it creates a nice line. And actually, if you go to the photograph, I'll go back again to the photograph. Again, sorry. Yeah. If you go to the photograph, you can actually see that line out here. Okay. Let me again go to the slide. Whatever this line was there, this line is actually reproduced as it is from the CAD data. Okay. This was done purely with HSS. So if you look again at the part, you had got one toolpath, you had got the second toolpath out here, and the third toolpath. Okay, sorry. Yeah, one, and then the other toolpath. So you can see that each of the surfaces were picked up separately and they were machined. And the best part of this particular model is, because many a times customers have asked me, can we know how this was machined? Of course you can know. If you go to our Facebook page of SolidCAM, you will see that this particular part and the related document, that means how to machine this part step by step, is actually available on our Facebook, including this part. So if anybody wants, they can download the SLD PRT of this, the related post, and the PDF file, which tells you how to machine this step by step completely with every parameter, everything explained inside. It's a pretty big book. It's like about 120 pages book. Okay, you can download it for free from our Facebook page. All right, let's look at another example. What's the other example? The other example here is, I want to show you some features of how SolidCAM works with parts with undercut. Okay, so let's do a curvature, not curvature, sorry. Let's edit this part and let's do a draft angle analysis with this as my main draw direction. You can see that, sorry, this area here is actually an undercut. It's almost like 8.5 degree undercut. Okay. Now this could be machined using our positional 5-axis. That means I could tilt this part and cut it, but that will need another attachment. It would mean to invest $100,000 or more into some machine which is already having this attachment, or buying that attachment. If the part is too large, then you can't put it on the attachment. You need to have that particular machine. So if you want to cut undercuts, now remember that you can't have undercuts of 45 degrees and expect it to be handled by HSS. Of course, it's possible, provided you use the dovetail cutters. It is still possible, but let's be more practical. If the undercut is such that could be handled by a slot mill or by a lollipop cutter, then trust that HSS is going to do the work for you. Okay, what I've done here only is that you need to be a bit careful. this surface was actually one single surface. Okay, so what I did was I just sliced, or I split the surface along this fillet, so that I get a good homogeneous surface out here to work with, and then I can handle this surfaces separately after we finish the top surface. So what we're going to do here is we're going to add HSS, and we'll use morph between two curves. I already have the geometry here. These are the faces that I'm going to cut. Okay. The start edge is this contour. Okay. And the end edge curve is that one. All right. And let's start and end exactly at the surface edge. Let's use a tool. So I'm going to use a slot and mill which looks like this. Okay. The diameter here is 18 with a corner radius of 3, and I've said my total cutting length is 6 millimeters. So I'm using a torus kind of a cutter to cut the wall. Okay. Let's select levels. You go by what is the default. Okay, fair enough. Let's calculate. Okay, that's done. So we have our toolpath. We have some retracts. Now these retracts, okay, are basically retracts that are connecting from one toolpath to the other. So this can be easily controlled inside our link page. So let's go to link and increase this value, let's say to 500%, and calculate again. Okay, that's done. Since this is about 8.5 degrees, you can see that the toolpath has been generated. But what we are not sure is if I run the simulation, okay, let's take it down so that we are more clear on what we are doing. Okay, I'm going to stop at this portion. What I'm not very clear here is what is actually going to happen. What is actually going to happen with my arbor? Is it going to touch the wall or is it not going to touch the wall? So here comes the powerful gouge check options of HSS. What we are going to do here is I'm going to edit and go to the gouge check. My first gouge check will actually make sure that the arbor is not going to touch any of these surfaces. Okay, so remember that when you're using a torus kind of a cutter or a lollipop kind of a cutter, you just have to have the tooltip enabled. It doesn't have a tool shaft, it only has an arbor. Okay, you have an arbor and a tooltip. Now I want to check against the drive surface. What should it do if it finds that the arbor is touching the wall or the drive surface? In that case, I would like it to retract. But how? If you look, I want to push the tool in this direction or in Y negative direction. So I can always retract the tool along -Y. Okay. And let's hit save and calculate. Okay. It's now pretty clear that this toolpath has now been checked for gouges against any collisions of that arbor and this drive surfaces. However, we also have another problem here, because if you see, let me run the simulation again. Let's go down slightly. Oops. Sorry. Okay, let's go. Forward. Okay, you can see that when it's here, there's every chance that my tool will end up colliding against these surfaces out here. Okay, so I need to now make sure that the tool doesn't collide against those surfaces. So I can provide in HSS a second group of check surfaces. So I'll enable, but this time I'm only going to enable the tooltip because I'm just worried about the tooltip colliding against the check surfaces. And let's pick faces 1. These are all the surfaces that against which I want the tooltip to be checked. And I want it to stay away from this particular surfaces by about 0.2 millimeters. So I don't want the tooltip to go and just stick to that surface. It should stay away by about 0.2 millimeters. Okay. Let's hit save and calculate. Oh, sorry. The strategy here is going to be trim and relink, and we are going to only trim the tool collisions. Let's calculate. Okay. That's done. Let's look at how a tool path looks like. You can see that it's nicely trimmed the tool path on the collisions. Okay, very nicely trimmed it along the collisions. So we can be sure that my tool is away from all these surfaces by at least about 0.2 millimeter. So these are some of the powerful gout check options that we have inside SolidCAM's HSS module. Okay, let's look at some other examples. The other example, what I was going to talk to you about was this particular part, where I explained to you about machining of the fillet. Now, you can look at this fillet here. Okay, if I mark the surfaces, although it looks very simple, it's really very difficult for us to machine this in HSM. If you just want to machine this portion of it, finding out the boundary itself is a major task. And you can see how HSS handles these areas. Okay, it's machining from this direction. It's going all around, finishes only this area and comes out. Now, if you look at the context of fillet machining, okay, I'll show you a more complex example, and I'll show you a difference between what would happen if you machine the same thing in HSM and the result with HSS. Okay, let's open a file. Okay, it's 5. You know this example even from my images out there. Now I would like to machine these pink surfaces that you see on your screen. Okay, I'm going to assume that I don't have HSS with me. I would like to machine this with HSM. To machine with HSM, first of all, we need a boundary. Okay, so I'm going to add 3D HSM, and we are going to use the same strategy, morph between two curves. So we have morphed machining in HSM. Let's define the tool. We'll use the same tool. I'm using a 4mm ball nose. Drive boundary. Since I have already defined this boundary for HSS, I'm going to use the same boundaries. So my first curve will be contour 1. And, sorry, this is contour, and then it's going to be contour 1. Okay. It's going to be along, and the boundary I can say is centered. Okay, we will see both the conditions. Constraint boundary, I am going to create a constraint boundary based on the selected faces. So I already have that boundary with me. So I'm going to click on show. You can see that boundary created by HSM passes. I just like to give a step over of 0.1. Okay, link bidirectional, retracts minimum, and let's calculate. Let's look at how the toolpath looks like. You can see, first thing, it started out here, but it has not exactly started at the edge. And it has stopped right here. Why? Because when you're machining with HSM, what it basically does is it goes to the top view and then tries to figure out what is the start point and what is the end point. So if I look from top, my end point is out here, but it can't stop the cutter exactly there, so it stops it slightly inside. But when we actually rotate it, it would have stopped much above the actual surface. This is one of the serious drawbacks when you go with triangulated machining. The other problem comes up when you have absolute vertical wall. Okay, when you have absolute vertical wall, the boundary creation gets really complex. Although it's a simple area, it really gets complex. And what we see in the end is result like this. So sometimes changing the boundary condition to external can help, but then you really don't know what is the right value, okay, where it can actually help you. It still isn't helping, but what has helped here is it has slightly pulled the toolpath outside, but you still don't know where it is exactly going to stop. Okay, so then starts the game. I call it a game of playing with the offset value. Okay, we start playing with the offset value, but again, it doesn't solve the problem of straight walls. Okay, it only starts increasing sidewards, but your straight wall still has a problem. Okay, let's look at the same solution offered by HSS. With HSS, it's pretty simple. I have these faces, okay, the same curves, the same tool, and I calculate. Quick, you can see the start and end, and look how it has handled the straight wall. So machining a complex fillet like this inside HSS is a breeze. It just doesn't take time. It works fantastic. You don't have to spend a lot of time. In fact, even the training time of HSS is about 1 or 2 days. The person is up and running, and what I have generally seen with my users is once they know the power of HSS, they try and machine maximum areas with HSS. They themselves try and isolate maximum areas with HSS. They use HSM also, but some areas which they feel they need to do much better, they use HSS. So HSS is really the crucial link between getting a good surface quality to getting an exceptional surface quality. It's a very crucial link, and machining local areas. Okay, I'll show you another method, another feature about HSS. So let me open another part. Simple part. In fact, the simple parts are the ones that consume a lot of time in machining. I would like to machine this particular, let's look at the display. Okay. I would like to machine this surface. Okay. Now this surface already has a lot of holes inside. With HSS, it's pretty simple. Okay, I'll add HSS and use, either I can use constant Z, which is pretty simple. So I just use constant Z. The geometry, I'll just pick the surface. Okay, start and end at exact surface edges. Pick the tool. Okay, it's a bull nose. Okay, and the tool path, 1 millimeter depth of cut, zigzag, tool control, everything is auto, and let's calculate this. Okay, let's look at the result. You can see, as usual, wherever there has been a cutout, the tool is retracting. Basically, it's telling me that these are gaps, and you need to handle them using smart links. So let's go and edit this and use in a link. I will increase the gap size. I can say 20%, or I can say, let's say 75% of the tool diameter as a gap that could be just connected directly. And these problems or these retracts that you're seeing can be controlled by just increasing the link between slices, the value of link between slices. Okay, so that's done. You can see that without having to close or patch up certain areas, we could easily create a toolpath which will exactly machine the surface, starting at the exact edge, and it will finish at the exact edge without the need of defining any kind of boundaries. What else can we do? We can do a lot of magic with this. For example, if these are my links and I would like to join them using a tangential kind of a links or a rounded kind of links, so I can say blend a spline between these passes. So you can see that I created immediately a blended spline between each of these passes. Since the tool is exactly ending on this edge, and these connections are also going to be on the surface, it is bad. So I would like to extend the toolpath on either side by a value of about 5 millimeter. Okay, let's calculate. You can see that the toolpath was pulled out of its surface by 5 millimeter. So my link is now going to happen in air and it won't happen on the part. Let's look at the entry. The entry is directly plunging on the part. Okay. Now I could provide a different kind of an entry. So I'm going to provide a lead-in and a lead-out. What is the kind of lead-in? I would like to have a tangential lead-in with 0 and another tangential lead-out with the same value. Let's calculate, and you can see that we provided a nice tangential lead-in and lead-out. Sometimes you have material still remaining and you would not like to have a simple tangential entry, but you would like to have a ramp into the part. That's also possible, although this is not direct. It's a small trick inside HSS. We go to the tangential arc, and instead of 90 degrees, I'm going to say 1200 degrees. I'm increasing the arc sweep, and I provide 3 millimeters as a height. Okay, okay, and calculate. And what I get here is a nice helical entry into the part. You can look at what are the possibilities of things that you can do inside HSS. Right. Now what we'll do is we will take an output of this, generate a G code. Okay, and it will open up Simco and I'll do a backplot. Let's change the colors. Backplot. Okay. Okay, so that's the toolpath that I have. And if I show you the points, you can see how the points are. You have a start point here, there's nothing in between, and you straight away have an end point. So this is one line. Now sometimes if you have a very sophisticated kind of a machine which has got its acceleration and deceleration not great, but it's there, and if that is kicking in, you will see that if you're given a feed rate of 1000, it'll take some time before it achieves the 1000 feed rate, and then it goes 1000 and it starts again decelerating towards the end. This can cause surface finish issues on your surface. You will see 3 different patches with different surface finish. In order to avoid that, what we can do, because you can't have just 2 points on that. So in HSS, it allows you to define your point spacing, which means you could define spacing of 2 millimeters between the point. Okay, and let's save and calculate and generate a G code again. Let's do a back plot. Okay, again you have got the smooth path, and if I now look at the points, you can see that it's now more evenly distributed on the part. So you won't have that problem of acceleration and deceleration coming in. Your surface finish is going to be much more smoother. It's much more uniform on the entire surface. So you can look at the kind of possibilities that HSS gives you to do any kind of part. It could be the most simplest part, or it could be the most complex part, but you can do possibly anything with HSS. Another very important thing in HSS is the ability to do feed control. For example, let's edit this, and I would like to create a sketch. Okay, let's create a simple sketch out here. And what I'm going to do here is insert, extrude this, 25, and direction to also about 50. Okay, so I've got a solid. I'm going to merge it. So for some reason you want that whatever feed I've given, for example in this I've given a feed rate. Let's define a feed rate of 1000. Okay, this feed rate of 500, retract of 5000. Okay, so in HSS you also have got a nice feature which allows you to define a zone for controlling your feed rate. For example, I'm going to define the zone. The zone will be defined by this entire cube of surfaces. So all 6 surfaces I'm going to define. Okay, and I will say the feed rate inside this should drop to 75%. Okay, accept and calculate. Okay, let's switch off that solid body and let's look at the simulation. Okay, let's take this. Okay, the feed is still 1000. The first cut feed, you can see that moment it came into that zone, the feed rate automatically dropped down to 750 because I asked it to drop to 75% of the feed. The moment it leaves that zone, it goes back again to 1000. So imagine what are the possibilities that you can do. For example, you have got a pocket and you would like the feed rates to drop down on the corners. You just create 4 extruded bodies and say that these are the zones where I want my feed rate to go down 50%. And HSS will automatically reduce that feed rate. So if I generate a G code, okay, I could calculate where is F750. You can see that it's put F750 straight away. So if I do a backplot and if I run where is F750, you can see that's the zone. That is the zone where you've defined the block. So all these areas, it's going to be 750 and then you have got 1000. So very important, you can virtually do anything inside HSS. Okay, so if I have to give you some kind of a gist, some kind of a summary at the end, first of all, it works in NURBS data. You can machine any kind of surface or any kind of part. You can cut any kind of undercut, provided it fits within the tool geometry. You can do a lot of internal tweaks to the tool path to machine it exactly the way you want to do it. Okay, it is not going to force you to do its own method, but it will allow you to define your own method when you are especially doing parts like this. Okay, most important thing, like I said, it's a crucial link between your 2.5D and HSM. HSS is a must. Without HSS, you could have several areas where you could see that, oh, I would like to machine it in this way, but I don't seem to get a solution. That's where HSS comes into picture. You will immediately find a solution with HSS. With this, I will end the webinar today, and it was really nice having you on board. If there are any questions, you could simply ask me the question or just type in your question so that I can reply.
Okay, Amo, thank you very much. Actually, there are two questions. One of them you answered already. I just read them both off to you. The first one was, what controls do you have to avoid the tool diving down into holes, etc.? And then the second question was, well, it said that you have answered my question about avoiding dives and retracts. Does this work on compound curved surfaces or when a hole crosses the joint of two or more surfaces?
If you're talking about cutouts on surfaces, compound surfaces, and if you would like the tool to avoid it, it's possible. It's straight away possible. For example, you saw that in the link I have got an option called direct or blend spline. There's another option called as follow surface. It's actually going to follow the curvature of the surface, even if the surface is not there, because internally it creates its own surface and it will follow that surface so that it doesn't dip into the holes or gaps.
Okay, Amod, this was a very enlightening webinar. I also learned a couple of things from it while listening to it. Thank you very much. Again, everyone, this webinar has been recorded and will be available again on our website tomorrow. Thank you for joining us, and thank you again, Amod, for giving this webinar.
Welcome. Thank you.
All right, take care, everyone. Have a great weekend.